All right. Welcome to part two. For those of you that were not here for part one, shame on you. You've brought dishonor to your families. No, but we talked about the discovery of X-rays, where they are, where they came from, what they do, how they, a little bit about how they are produced. We talked about the basics of the radiographic imaging room, how an X-ray tube functions in a general sense, and things like focal spot size, stuff like that. So we said that we are going to be operating in that 40 to 150 kV range, and that it would allow us to produce X-rays of shorter and shorter and shorter wavelength, higher and higher and higher frequency, the higher we go in kV. So with your kV selection, what did we say we were going to base kV selection on in general? Well, not mass like atomic mass, but patient thickness, right? Yeah, don't overthink it. All right. Yeah, patient thickness. And so the higher we go in kV, the more penetrating ability we have. But we're talking about some pretty high voltages here. One of the reasons that our system is as insulated as it is that 150 kV, in case you didn't know, will arc through 4 feet of air. So that'll reach out and touch someone. So yeah, we want to treat it with respect. Also, when we get inside of some of these cabinets, you're looking at somewhere in the 400 to 800 volt DC range for a lot of these power supplies on the primary side. So they mean business, right? But we started talking about one of the most important parts of this whole situation here, and that was quantity and quality. And we said that when we were talking about these, we were speaking about beam quantity and beam quality. And that it had to do with, well, how much radiation was being produced, the quantity side, and how penetrating that beam was. And the one thing that that had an effect on both of those was, in fact, the kinetic energy, or the kV, that we apply to the X-ray tube. Of course, the number of electrons that we have at the cathode would contribute to quantity, as would how long we left that tube on. We said that our system was horribly inefficient, that we turned most of our energy into nothing other than heat, but that some of it got turned into X-rays. And there's a couple of ways by which that can happen, all right? Now, I'm going to blow through this pretty quick here. So if you have questions, and I should have said that in the first part. If anybody has a question at any point, ask. I mean, it's why you're here, it's why I'm here, right? It's kind of like what I do, right? So it's answer people's questions. So if anything pops up along the way, let me know. When we are creating X-rays, we're talking about the interactions of electrons in matter. Now, we said that if we were trying to make these X-rays, we would be hurling electrons at a target. That target, of course, was tungsten. And if that incident electron, which comes screaming in here with a negative charge, passes close to the nucleus of a target atom, which is positively charged, that it would cause it to change direction, right? And when it does that, it has to give up some energy. It's going to give up that energy in the form of a Bremsstrahlung photon. Bremsstrahlung is German, quite literally, for breaking radiation. Not like breaking, but breaking, okay? When that electron changes directions, it's got to slow down. Just like when you're driving in a car, you want to make a sharp turn, generally you hit the brakes first. In that case, you're converting the kinetic energy of the vehicle into heat in the brakes. Here, you are converting that kinetic energy into an X-ray photon of some energy, all right? The energy that's created here, really, all that it depends on is how close we pass to the nucleus. All right, here's the real fun part. None of this involves a collision. That electron didn't interact with anything, right? So it's just like, you know, when Kim walks through a room and smiles, it's an interaction, right? spreading joy. But, she didn't smack anybody upside the head. So there was no physical interaction. Same thing here. The closer we pass to that nucleus, the more energy we can give up to and including the total energy of that incident electron. So if I am applying 100 kV to an X-ray tube, 100,000 volts, that means that at my cathode, I've generated a space charge, I've heated up that filament in that 6 to 12 volt, 4 to 5.5 amp range. So I've got a cloud of electrons there. When I go to expose, that's when I apply the high voltage. The negative charge is going to repel the electrons from the cathode. The positive charge is going to attract them to the anode. And when they have these interactions, one of the interactions they can have is this Bremsstrahlung interaction. And that 100 kV photon, well, it might have a relatively sharp interaction here. Let's say it gives up a photon with 70 kV of potential, 70 kV of energy. Well, that electron still has 30 kV left. So that can go on to have other interactions that might be converted into heat. It might be converted into another low energy, now much lower energy photon, right? Or we could pass very, very close to the nucleus and we might produce a very, very short wavelength, 100 kV photon, or farther out and produce one with a longer wavelength. This is how we end up with this setup with a broad spectrum of radiation being produced, what we call a polyenergetic beam. Many wavelengths and many frequencies. And if you look at that spectrum, you would see that at the lower end of the energy range, if we use this corner of our slide as that as the y-axis here as our quantity and the quality or the wavelength down here, you'd see that down here at the very lower end, we have a whole bunch of radiation being produced. And as we get closer and closer to the peak, we'd see less and less and less and less. The reason for that is because of the likelihood of these interactions to occur. All right? It's very, very difficult for an electron to get very, very close to the nucleus. So just in general, I'm going to have not very many of those interactions happening. But I'm going to have a whole bunch of interactions happening out here in the outer reaches, as it were, all right? So when that occurs, I end up with all of these electrons that still have kinetic energy to give up. So they're going to have other interactions until they give up all that energy, all right? That's a good example. Let's see. Anybody else cook? Yeah. Nobody? What's the matter with you people? I grew up in the restaurant business, and I mentioned earlier, my wife refers to Facebook as David's cooking show. And if somebody gave me, I don't know, $1,000 and sent me into Sur La Table store with, really high-end cookware, cook gear, chef's knives, all that good stuff. Well, that $1,000, that's a lot of potential, right? And when I go in there and I interact with Sur La Table, when I leave, that $1,000 is going to be gone, but I'm going to have some cool stuff. All right, here, the kinetic energy is that $1,000. That 100 kV is the energy that we're giving that electron. It's going to give up all of that kinetic energy eventually. It's just like if you roll a ball down the sidewalk, eventually the ball is going to stop, right? It's going to give up all that energy and just stop moving through rolling resistance and other interactions. So what happens to that electron? Oh, nobody said there was going to be a quiz. Here's a question. What do we do in electronics? We push electrons around, right? We give them potential, we take it away, we make them do work, right? Nothing happens to that electron. It continues on as part of the circuit. The only thing that happened in that X-ray tube was we generated an electron, we gave it a bunch of kinetic energy, and we threw it at something. When it hit that thing, it gave it all up, either in the form of heat or in some teeny tiny fraction, the production of some X-rays, right? So that's one type. There you go, they go through the whole thing there. Another type, oh, they left it out. Huh. All right, so with the characteristic radiation, they've got the wrong slide here. I need to talk to them about that. Characteristic radiation is different. They're still, I don't know how this ended up with the Bremsstrahlung in there, but imagine we had an electron that came in here and actually knocked this electron out of its orbit. That would create a void, it would create a vacancy. The atom would not like that, so it would fill that vacancy by moving electrons down from higher orbits. It might happen in a single leap, or it might happen in multiple jumps. Either way, it's going to fill that spot. And when it does, as these electrons change orbit, they're going to have to give up some energy. They're going to give it up in the form of an X-ray photon, and that photon is going to be characteristic of the binding energies of that element, right? So we talked about that big broad spectrum that we were going to produce. Well, you'd also get some characteristic spikes in there based off of the various K shell, L shell, M shell energies that are happening there. All right. So which one's more important to us? Bremsstrahlung or characteristic? Well, but here's the deal. Bottom line is, it depends on what we're trying to image. If all of my characteristic spikes all happen below or above the range that I need for a combination of penetration and absorption in my subject, then characteristic radiation doesn't help me at all. When we're talking about general rad, Bremsstrahlung is where it's at, because we're looking at lots of different types of anatomy, lots of different structures. So we need that flexibility, because we can control how much we're getting, right? We can control how much radiation we're getting, and we can control which part of the spectrum we're getting it from. We can even remove the stuff that's too soft. In fact, we do by adding filtration to the beam, because that stuff that's super soft is not going to contribute to the formation of the image. It's just going to give more dose to the patient, right? So we get rid of it. Now, if you're talking about things like specific studies where they always look at the same tissue all the time, like mammography, right? In mammography, we're imaging adipose, glandular, and fibrous tissues that are all extremely close in physical density. It's like 0.92, 0.93, and 0.95 or something like that. I mean, they're very, very, very close, which means it's difficult to get any visual separation between them. In that case, yes, they're very, very interested in like the K shell energy of the materials that they're using. In fact, not all mammo systems use tungsten as their anode material, right? They may use molybdenum or rhodium, or they may use tungsten with molybdenum and rhodium filters, sometimes silver. It's a whole different thing, right? So yeah, one of the phrases that you'll hear a lot in diagnostic imaging to why do we do it this way is it depends. Because it really does. It depends on what we're looking for, what we're trying to see, and who's trying to see it. I mentioned that when we get into the factors affecting radiographic quality, that's a huge deal. And one of the big things we talk about is image contrast. And with image contrast, well, you have image contrast, you have subject contrast, and you have contrast resolution. Right? Image contrast. Well, what's good, high contrast or low contrast? It depends. It depends on who you're talking to and what they're trying to see. All right. So here we have a complete insert. This is actually the RAD99 insert out of an OEC surgical C-arm X-ray tube. And this is everything that would be inside that housing except for the oil. Right? So we have the glass envelope itself. We can see our nice shiny cathode there, our anode. We've got a pair of filaments in there. They're both pointed, aimed, I guess you would say, at the same spot so that our central ray remains the same. And that is attached to the shaft with the rotor in there. Of course, the rotor is inside the glass. Outside the glass, we have the stator. The stator windings, there's nothing mystical about them. I mean, it's the stator rotor relationship is no more complex than like a ceiling fan. It's just an AC induction motor. You know, they come in lots of different setups. You've got regular, Q, E, three-phase, all kinds of stuff. But essentially, they're all going to do the same thing. They're going to spin that anode. Anode rotation, by the way, in case you didn't know, 99.99999% of the time, anode rotation will be counterclockwise. What do you suppose it's counterclockwise? Counterclockwise from the perspective of the cathode. So if we were looking at it this direction, it would be rotating. This nearest face would be going up. I'll give you a hint. They do not rotate clockwise in the southern hemisphere. No, although I like that guess. Somebody's got it. Somebody's got it. All right. I don't have one here to hand it to you, but if I handed it to you and you looked at it, you go. That's why I said it doesn't rotate in the opposite direction in the southern hemisphere. If you were to look at this, you notice that the anode is held onto the shaft by a nut with a right-handed thread. So we rotate it counterclockwise so that it's constantly tightening that nut. Now there are Siemens, some of their tubes, the anode is actually swaged, actually press, deform the shaft so that it's press fit onto there. It can go either direction, it doesn't care. And most modern tubes, I mean, you have pins that will take a lot of the torque. You have lock washers, they stake the threads, actually deform the threads to mechanically lock them. The chances of one of those coming off is fairly slim, but it's not 100%. All right. Just recently, I had a student said that they went in to check on a room. Tech said the room was making funny noise and her images were coming out blank. They walked into the room. They looked at the table, they noticed a few drops of oil on the table. Well, outside of this, inside that housing, it's filled with dielectric oil. It's filled with transformer oil. Because again, this thing will go up to 150 kV. It'll arc through 4 feet of air. So the oil doesn't help with temperature stuff, sure, but it's really about electrical insulation, right? He's like, well, oil's supposed to be in there. So he asked the tech, said, have you done anything? They said, no, it made a noise and we knew something was wrong, so we just called. So he walked in there and he looked at the table again and he looked at the tube very, very carefully and he could see a very fine crack in the housing of the tube. And then he turned around and looked at the opposite wall and there was a hole in the wall with this profile. Because it was a high-speed tube. So that anode, either the shaft broke or whatever happened, but that anode came off of the shaft going 10,000 RPM. So you've got about 3.5, 4 pounds of tungsten going 10,000 RPM. That's a lot of energy. When it comes off of that shaft, that housing is not going to stop it. And it flew through the side of that housing so fast that the housing just went like that. It cracked it, and then it bent enough to let the anode out and then sealed itself back up. That's why he only had a little bit of oil on the table, right? So they never did find the anode. It was on an exterior wall, and they don't know what happened to it. What's that? Oh God, yeah, yeah. No. It wasn't that the glass had. It was remember, this is all inside a metal housing, right? So it was the fact that this had come off of the shaft had broken like right here. Yeah. The metal housing had the glass was, yeah, gone. Yeah, which brings up another point. If one of the phrases that we use all the time when installing systems is don't drop the baby, right? Don't drop the baby. So if you ever take an X-ray tube out of its shipping container and it sounds like a slushy maraca, don't bother installing it. Something bad happened to it on its way to the forum. All right. So yeah, it's inside this housing. And that housing, well, you can kind of see where this gets a little bit thicker right there. That's the lead lining. There's actually a big sheet of lead right here, but it's usually like aluminum or pot metal or whatever they make it out of. It's a cast housing that's then machined. And right down here we have the port of the X-ray tube. So that's why I said we always see that X-ray beam drawn as a cone coming out of there, and that's because this is the one place we let it out. All right. This solid piece here, that is the port of the tube. It's actually transparent. You can actually see through it. This part is lead as well, what we call an off-focus cone. It helps to reduce the amount of off-focus radiation. You can actually see the square port right there. But yeah, so it does the trick. Now this one is, it's not that same insert that we were just looking at, but you can see the stator windings down there, the anode, the cathode. Now, one thing you may note in looking at these is one has a cathode on the right, the other has a cathode on the left. Or another way to put that is this one has the anode on the right, this one has the anode on the left. There are right-handed and left-handed tubes. Okay. And when they say that, they're referring to it in terms of which side of the tube the anode is on. Okay. When I'm checking things, if I'm checking for an open filament, stuff like that, I need to check the cathode side of the tube, of course. But I want to know which side that is. Usually it's labeled, but not always. But a quick and dirty way to tell often is when you walk into the room, if you're standing in front of the table looking at the X-ray system and the tube, look to see which side of the room the wall stand is on. Whichever side of the room the wall stand is on, typically, not always, that's the side of the room that the anode will be on. So if your wall stands to the right, you've probably got a right-handed tube. If your wall stand is on the left, you've probably got a left-handed tube. Why would we do that? Oh. Generator's closer. Nope, it's a little more complicated than that. Even though we are producing a heterogeneous, unmodulated beam of X-rays with many, many different wavelengths and frequencies, the intensity of that beam is not the same across the entire beam, right? And I don't know if I have something here I can show you that with. Oh, let's go back. Yeah, this will be better, all right? So if we think of the beam that we're letting out as coming off of here, the intensity of the beam will actually drop as we get closer to the anode. In fact, in the area of the anode is where it is the least intense, but also the hardest, all right? Something they call heel effect. We don't talk a whole lot about heel effect, or you probably haven't heard a whole lot about it, because in modern digital imaging, we calibrate it out of the image, all right? If you were to look at an actual film image, you could actually, in some cases, see the heel effect. You'd see the darkness of the film drop off as you move toward the heel. The reason we have right-handed and left-handed tubes is for patient safety. When you have a patient standing at the wall, you want the hardest part of the beam that's going through their chest to be closest to their brain. All right? So if we rotate the tube so that the anode is up, the hardest part of the beam is going to be closest to the brain. That makes sense? No? We're going a little too fast? It's a lot of stuff. A lot of stuff in it, very sure. Yeah, yeah. Well, I mean, in general, it's the more penetration we have up there, the less absorption and scatter we have. So, yeah, it's about attempting to reduce the amount of scatter that's being produced by the subject, because anytime X-rays encounter matter, you're going to get penetration, you're going to get absorption, you're going to get scatter. It's just the way it is. I don't care if you're shooting a block of lead. You know, lead is what we use as a medium to prevent the passage of X-rays, right? But when those X-rays hit that lead, they're still making scatter. Right? So, yeah, it's we just want the hardest part of the beam up there. Now, and like I said, in modern digital imaging, that variation, we actually calibrate that out. Have any of you ever heard of a flat field calibration, right, on a DR system? That's where it has you filter the beam and take 10 or 20 exposures, and it actually adjusts the gain across the entire image receptor so that it evens everything out and makes the heel effect go away. Right? So it's almost like, well, when you go to the dentist, they put a lead apron on your body to protect your body from the scatter your face is making, right? So weird to think of it that way, but there you have it, all right? So another way that we can protect the patient is by adding filtration. Filtration serves a couple of purposes. The main one is that it reduces dose to the patient. We said that we're going to produce this broad spectrum of radiation, but that the softest radiation doesn't do anything at all for us. All it's going to do is be absorbed by the patient, lead to more dose. So if we add some filters, well, aluminum in particular tends to absorb radiation in the longest wavelengths first, right? Or if you want to put that in a more scientific way, it attenuates the beam primarily via the photoelectric effect, right? Which is a fancy way of saying it stops the soft stuff. Right? But it does something else. It also affects, yes, sir. Or long wavelength and short wavelength, right? Because you're going to get across the beam, you're going to get up to whatever your peak kV is, but you're also going to get everything below that. Yeah. So if you think of it like if you got a string of lights, and in order to make the top light light up, we have to light up all the ones below it, right? So, you know, wherever we stop, that's going to be the peak, but we still have to have everything below it as well. Yes. Yep. Yeah. KV. Well, it's both really, because the higher the KV we apply, the shorter the wavelength and the higher the frequency of the photons that are produced. And the shorter the wavelength and the higher the frequency of the photons that we produce, the more penetrating they are. Yeah. Yep. Right. Is there something else? Thought I saw another. Okay. All right. So the other part of this is aluminum. Aluminum atomic number 13. All right. Now that's the atomic number of an element. That's the number of protons in a nucleus. In diagnostic imaging, it's also referred to as its Z. When we talk about biological tissues, we refer to their Z effective. They effectively act like blah, 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 right? So adipose or fat has a Z effective of 5.92, which puts it just below carbon at 6, which makes sense, carbon-based life forms, right? Muscle has a Z effective of 7.42. More dense than fat, right? Or higher Z than fat, but it's made up of different stuff. Both muscle and water have the exact same physical density. They both have a physical density of 1. But if fat is at 5.92 and muscle is at 7.42, bone, which is what we're often trying to see, is at 13.8. Where do we say aluminum was? 13, right? So if aluminum is above adipose and muscle and below bone, here's the deal. In diagnostic imaging, anytime my filter has a higher Z than another structure, it tends to make that structure more transparent. So aluminum is a preferred material for a number of reasons. It's really good at stopping soft radiation, and it's really good at making bone stand out in the image. And what if we don't want to see the bone? Ooh. We don't want to see the bone, then we have to use something else that has a Z higher than bone. Copper. Copper is 29, I think, on the periodic table. Somebody can Google it, correct me if I'm wrong. Should be right around 29. Google at 20, Google at 29. Yeah, copper at 29 has a higher Z than bone, right? So in things like cardiac catheterization procedures, if they want to look at the blood vessels of the heart, what don't they want to see? They don't want to see the rib cage. They don't want to see the sternum, right? They're shooting from the back. They don't want to see the thoracic spine. They want that all to go away, right? So they use copper as the filter to make the bone transparent. Well, if copper at 29 is making bone at 13.8 transparent, what's it doing to the heart at 7.42? Heart's invisible. Right. You might be able to see a faint shadow of where the heart might be in the image. So what the heck do we do? Contrast. Yeah, we inject contrast. For cardiac work, veins, arteries, heart valves, all that stuff, we use iodine. Iodine is up there at 53. So way above that. Oh, sorry. My wife's walking the dog. Question? Yeah, yeah. The iodine at 53. And if we're doing things like intestinal studies, upper GIs, lower GIs, they're going to use barium sulfate. Barium is 56. So way up there, right? Going to really help that stuff stand out. So yeah, if we want to see something that's difficult to see in a paradoxical way, we make it harder to see and then we make it easier to see. We make it invisible and then we bring back what we want to see by adding some contrast. Right? So those filters, sometimes they're right in the collimator, sometimes they're up in the port of the tube, sometimes they're adjustable on things like the Definium 8000, XR656, some of the GE rooms. You can select right from the console, and you'll hear these little solenoid-driven filters move in and out inside the collimator. In that case, they do something a little bit different. Because the digital receptor can get away with a harder beam, they just use copper, right? But they use a teeny tiny bit of copper. So instead of using a millimeter or 2 millimeters of aluminum, they might use like 0.02 millimeters of copper, something like that. So that's another twist on that whole thing, is that you can use a smaller amount of a higher Z material to equal a lot of a lower Z material. All right, if that tracks. Oh, the filter? Yes. Yeah. Yeah, screens are a different thing. No, no. Mammo, there you're going to see molybdenum, rhodium, silver. Yeah, lots of different stuff. Again, they're more interested in, or they have a keener interest in the characteristic radiation. They still need the Bremsstrahlung, but they want to tune it more because they can. general rad, we don't have that opportunity generally because we're looking at so much different stuff. We might be doing, chest shot 1 minute and, a broken wrist the next. So they have to have that flexibility. Mammo, they're always looking at same tissues, same tissues, same tissues. So they can dial that in much, they can specialize, I guess would be a good way to put it. Yes, yeah, but like I said, they're usually going to be molybdenum or rhodium or silver. Or sometimes they'll either, because mammo also works in a completely different range, right? So instead of in the 20 to, what was it? Instead of the 40 to 150 kV range, they'll be in the 20 to 40 kV range. So much, 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 much lower kV. And since it's at lower energies, they don't necessarily have to have a solid tungsten target. So you will see some systems where the anode will be tungsten, but laid into it, they'll have inlaid into it a track of rhodium and a track of whatever they're using, right? So they can do it that way as well. So they can either use those specific materials to generate the X-rays, or they can filter the beam using those materials. Right? Oh, where'd I go? There we go. So the collimator, we said the collimator was a beam limiting device. The whole idea here is that we want to restrict the X-ray beam to the area of our image receptor. We mentioned the term PBL collimator last hour, and I just briefly said it. PBL means positive beam limitation. Fancy way to say an automatic collimator. It'll automatically size to the size of our image receptor under certain conditions, right? If I have my image receptor laying on the floor, the system has no idea what size it is. So I'd have to collimate manually at that point. But if I'm using the table bucky or the wall bucky, there I can, have it automatically size. Of course, I can override that if necessary. If there's a problem, there's usually a key switch that's used to bypass that mode. But most techs are lazy, so they're going to do what the system tells them to do. All right. And it's not, I don't know, that's not to disparage techs, because we know techs are always gentle with the equipment. But you'll find that kind of the holy grail of diagnostic imaging in general is to be able to have a system where we could put a patient on a table, press one button, and get an image. That'd be it, right? Or maybe not even on the table, just have them stand in a booth or whatever the case may be. But it's a little more complex than that, although it has been getting easier and easier and easier. It used to be the technologists had technique charts on the walls, and they had to dial in every setting and make every selection and all that good stuff. Now we have APRs, anatomically programmed radiography, what some manufacturers will call protocols. So when I start a new patient, Bob Ross, patient ID, happy trees, right? And I go ahead and want to start a study. Well, first I have to select my protocol. It's like, okay, I want to do a chest, and it's going to be one view. And so I select that, and boom, the system will say, oh, you're doing a chest, a single view. Well, that means you're going to use the wall stand at this distance, this source to image distance with this grid, and you're going to use automatic exposure control, and I'm automatically going to tell you which of the 3 chambers I'm going to use. And depending on whether you have a small, a medium, or a large patient, I will determine the KV that you're going to use. You might have to select that. And yeah, we can probably do this on the small focal spot, so we'll already have that selected for you. It's pre-selected everything for you, all right? So here's your takeaway from this afternoon. When you get involved with diagnostic imaging, if your systems give you some way to back up the protocols, to back up the APRs on that system, for the love of God, do it, right? Because someday they're going to lose them. Computer glitch, lightning strike, who knows, right? Mars is in retrograde, anything can happen. And if they lose those protocols, as far as they're concerned, the room is down. Like, no, you've got a technique chart right here. It's by law, you've got to have one. Just use that. We don't do that. We just say what we want and it does it for us. All right, because that's one of the downsides of that advancement is as they come to rely on it more and more and more, they forget how to do it. Oh God, yeah. Hmm. Right, right. And that's also that brings up another important point, and that is applications. Applications training, that's not us, right? On the field service side, on the imaging specialist side, um, we're there to fix imaging issues and to fix machines, but by law, we cannot tell them how to use it. I can explain the functions of a machine. I can say, if you press this button, it will do that, but I can't say you should do this on that patient. Unless you are a licensed rad tech, it is quite literally illegal for you to tell them how to use that machine, right? I don't know about you, but I don't want to be named in that lawsuit. When they say, well, Dave told me I could do that. Uh-uh. Right? So of course, for our over table tubes, this is going to provide us with a light source that's going to show us where the x-rays are going to fall. That's one of the calibrations that we do. A lot of people call it x-ray to light field adjustment, but it's actually the exact opposite, right? The x-ray field is going to be wherever it's going to be. It's our job to move the light field to match the x-ray field. And we're allowed, it's like 2% of source to image distance, 2% of SID in either direction, or 3% without regard to sign. So that seems like really, really tight tolerances, but it's not. If you're doing at a 40-inch SID, which is typical, that's like 0.8 of an inch. If you're if your system's metric and you're shooting at 100 centimeters, that's 2 centimeters. So you're allowed a pretty big margin. In fact, you're typically allowed way more than the techs will let you get away with, in my experience, on the federal level. All right. So we said that X-rays were going to do one of three things. They're going to penetrate, they're going to absorb, or they're going to scatter. Penetration, as we said, is the unimpeded passage of X-rays through matter, meaning they pass through like you weren't even there. They're going through the spaces between spaces. Absorption, here it says the complete loss of X-ray energy. Another way to think of that is it is the complete annihilation of an X-ray photon in matter. An X-ray photon comes in, smacks an orbital electron in one of the atoms in your body, and transfers all of its energy to that electron, ejecting it, causing an ionization event. Within that process, that photon's gone. If it is of sufficient energy, then we can get scatter. Scatter happens when that incident photon has so much energy that it ejects the electron, but it still has energy left over. That leftover energy is converted into a new, now relatively soft, longer wavelength photon that goes in some other direction. Right? So secondary radiation. Another thing to remember here is that when it comes to protection for ourselves, really, that's it, scatter is the main thing we're concerned with. There's no reason for us as field service folks ever to be in the primary beam. There just isn't. If you're curious about your image quality or curious about your resolution, we have phantoms for that. We have all these special tools that we can put in there, right? Because remember, 10%, right? 10% of that damage that gets done by any exposure to radiation is permanent, and it is cumulative. You know, I used to know an engineer, used to. Yeah, he's a really talented guy, did a whole lot of fluoro work, and instead of putting a line pair phantom in there, he just put his hand in there. Well, looks pretty good. A couple of adjustments. Right? Like, what are you doing? It's like, it's just a couple seconds. It's like, yeah, but it's a couple seconds. How many times a day? How many days a week? For how many years? He ended up with cancer in that arm. And yeah, his oncologist said it's a relatively aggressive form. We're probably going to have to amputate your arm. Well, you can't take me. He was a private pilot as well. I was like, can't take my arm. If you take my arm, I won't be able to fly my plane. So they didn't, and it eventually spread to the rest of his body. And within about 3 years, it killed him. So now he can fly with his harp. Yeah, no, I mean, it's silly because it's completely unnecessary. Oh, don't get me started. But no, I said don't get me started because the dosimeter, you know, your personal dosimeter is there to keep track, right? But I will tell you this, I was at a facility, had all my equipment set up. I was about to do a calibration run on a system which involved many, many exposures. I'm just about to get started and the tech goes walking into the room. Said, oh, I'll wait. They're like, no, man, it's cool. Go ahead. Like, excuse me, no, it's not cool. I'm not going to go ahead. It's like, no, really, it's fine. Said, no, it's not. It's, you know, I cannot make exposures while you were in that room. It's like, oh, come on, man. I got my badge. That's not what was going on here. I said, what exactly do you think that does? And he literally thought that his dosimeter was like a radiation magnet and that it would suck all the radiation to it and he wouldn't get any. So we had a nice long talk that consisted of him, that involved him going, oh, a lot. And then he stopped doing that dumb stuff, I hope. You know? But, you know, it's ionizing radiation. You can't see it, you can't feel it, you can't taste it. You know, what harm could it do? One of the things I have in my museum at RSTI is an X-ray shoe fitter. Right? Adrian X-ray used to make these. At one point, there were 10,000 of these things in the United States. It was a fluoroscopy system. Had a box, little Bobby or Susie trying their new Buster Browns. They'd hop up on there, put their feet in the hole in the box. They could look through here at a fluorescent screen. Mom or dad could look through one viewer. Salesperson could look through another one. They'd flip the switch, hit the button. You get about 20 seconds of fluoro time. Meanwhile, everything is in a highly shielded plywood box. So you're irradiating the piss out of everybody. Except I have a former student who has a kid, has to shoe store every day on his way to and from school. And they would run in there, look at their feet. He ended up with a deformed foot. So yeah, but, oh, and the real kicker was it was just a sales gimmick. The soft tissue of the foot has way more to do with how a shoe fits than your skeletal structure. So it served no purpose. All right. So of the three, we said we need a combination of penetration and absorption in order to generate an image. Scatter, we don't want. But we can deal with that somewhat with the use of grids, all right? Now, we talked about filters, and we're gonna talk a little bit about grids. When I said screens are different, screens usually refers to intensifying screens. That are, that's what's used in your CR cassettes, in your film cassettes, Well, in CR, it's europium, dope, barium, fluorohalide crystals, but that doesn't matter. In some of your DR panels, you have indirect DR panels that use cesium iodide crystals that convert the X-rays into light before they convert them into an image signal. But those are what we would refer to as screens. Grids, on the other hand, are also wrongly named because they aren't grids in most cases. There's one that is. But the original grids were. It was a grid of lead strips. It was stationary, it worked. It helped to prevent scatter from reaching the image receptor. The problem was that you had that grid image superimposed over everything. So then they came up with the linear grid, and this is what we're looking at here. These black lines here represent strips of lead, long strips of lead. So this thing could be maybe 17 inches by 17 inches, or 14 by 17, something like that. You'd have these long strips of lead with long strips of aluminum in between them. The whole idea being that these would allow much of the primary beam through, but any scatter that's being produced would hopefully be absorbed by the lead. They came in different ratios, basically how tall the strips were. That would affect the distances that you could use them at or their focal range, but they work. The other thing that they did was they figured out, hey, if we move that grid during the exposure, it'll blur those grid lines and they'll disappear. And then later on, when they got into digital imaging, they said, hey, we've got computers, so if it sees grid lines, we can say, make them go away. And it does. And then some digital receptor using manufacturers like Philips said, yeah, that's a bit much, so we're still going to use the moving grid because it's easier. There's less things to go wrong. All right, so these grids are the one thing, well, I shouldn't say the one thing, they're one of the only things that we use in diagnostic imaging that is not specifically designed to reduce dose to the patient. All right, filters reduce dose to the patient. Collimation reduces dose to the patient. You know, using harder X-ray beams reduces dose to the patient. Having faster receptors that need less dose reduces dose to the patient. We add a grid, more dose. All right, because we're taking a big sheet of metal and we're putting it in between our object and our image receptor. All right. So in order to compensate for its presence, I need to increase the output of the tube, which means the patient gets more dose. So for a typical table bucky type setup, maybe a 12-to-1 grid, you'd need about 5 times the dose that you would use without the grid to achieve a similar optical density in the image. Crazy stuff. These, yeah. The only major advancement that I've seen in these since, other than going from an aluminum face on the grid to a carbon fiber reinforced panel, would be Hologic when they developed the HTC grid, the high transmission cellular grid, which is used solely in mammography, solely on their systems because they patented it. And instead of lead, it's like 7 layers of a copper alloy, and instead of aluminum in between, it's air. So the high transmission part, the cellular, because it is a grid, but it's a grid that's rotated almost 45 degrees. It's a whole crazy thing. They're expensive. It's like $20,000 for one of those grids. Right? So here we get the idea. Now in this case, you can see all those, the strips are vertical, are lead grid strips. That's how they would be in the center of the grid. But with a focused grid like we have here, you can see how they kind of fan out as you move from the center toward the edge. Again, that is to match the angle of divergence of the beam itself. All right? Something happened. You're a winner. If we wanted to have them all like this, all vertical, then the grid itself wouldn't be able to be very thick, so it wouldn't be very efficient. but it would work over a very broad range of distances. All right. As far as image receptors go, film, not even going to bother. You're not going to use it. You're not going to see it. There's very, very little of it left in the United States. If you plan on traveling the world, yes, we can talk all about film. I could talk for a day about film. But the intensifying screens, that's what I was talking about earlier. The intensifying screens are a phosphorescent screen that really all they're doing is providing more opportunities for interaction, right? When you look at film itself, when we expose film to X-rays, this is just a further building of our lack of efficiency in this system. We put all this energy into the X-ray tube, less than 1% of it comes out as X-rays. Of that, less than 5% would actually interact with the film emulsion. So they invented intensifying screens, these phosphor screens, to provide more opportunities for interaction. An X-ray photon that didn't interact with the film might interact with the phosphor, which would generate some light that would help to expose the film. Right? Now, this same process of more opportunities for interaction is how some of our digital receptors work. Right? With CR systems, computed radiography, this does use a screen. Let's see, we have there we go. But in this case, it's using europium-doped barium fluorohalide crystals, and the europium is the magic part. All right? Because europium, with these barium fluorohalide crystals, when we expose one of these screens, you'll actually see it glow blue. That's because you're exciting these crystals, and close to half of them are returning to a stable state. When they return to a stable state, they give off blue light. But the other half don't. They stay in that excited state. It doesn't continue to glow. Well, I guess it does, but it's outside your perception. There isn't enough of them reacting slowly as they slowly give up that energy. The CR cassettes will hold on to an image for up to 24 hours. But if we then take that cassette and scan it with a red laser, that red laser will force those crystals back to a stable state, and they will give off blue light in proportion to the amount of radiation that they received. We can then send that up to a photomultiplier tube, convert that into an electrical signal, send that through A to D conversion, and create a digital image. CR as well, largely going away. All right. There are still places that will use it, but the federal government, in an effort to streamline things, there was a big push to get everybody to go DR. And the way that they encouraged that was by reducing the Medicare and Medicaid reimbursements for CR-based images. All right, so it hit them in the wallet, right? So what they did was, from one year to the next, they cut the reimbursement in half. The year after that, they cut that in half again, and the third year, it just went away altogether. So, but that doesn't mean CR has gone away everywhere. So things like native health services, private practice, vets, chiros, places like that, that don't rely on those reimbursements, they don't care. They're going to keep using them as long as they can because it's cheap, right? We've got a CR cassette there. It's about $1,000. Compare that to a DR detector, over $100,000, right? So that's the other thing. Everything in diagnostic imaging is expensive. What's that? One would hope so, but the bulk of the reduction in dose is a cumulative reduction in dose to the population as a whole due to the fact that we have fewer repeats. With film, if I take a shot and it doesn't come out, I got to shoot it again. I've been in teaching hospitals where I'd watched a student tech do a 10 film study on a patient, not one of them turned out. Well, they don't care, shoot them again, right? With CR and DR, as long as the data is there, I have post-processing. I can pull that information out, right? So overall, even though this acts more like, say, a 200 speed film, which would be a slow film, a 400 speed, which would be your average film speed, would use less dose than this. But if I have to use it 5 times, all right, then yeah, that's where a lot of that comes from. But I mean, detectors are getting better and better and better, so the dose will continue to reduce, I'm sure. All right. But of course, in doing that, we've got, gosh, things to think about as far as, how many pixels we have, our bit depth. This is all stuff that we get very deeply into in phase 1, 8-bit processing, 12-bit processing, 16, 32. What that really controls is how many shades of gray we have available to us. Oh, we're out of time. So last question. How many shades of gray can the human eye distinguish? And it's more than 50. 256. Yeah, you're absolutely right. Yeah, for a trained radiologist, they can distinguish about 256 shades of gray. So I have 12-bit processing that gives us 4,096 shades of gray. We window and level. Yeah, we can control which 256 we're seeing or which 256 we bring into our viewable range. So kind of nifty, right? Yeah. I'm not in any rush. So if people want to hang out, if you need to move on to your next thing or get a bite to eat or whatever, that's fine. But yeah, if anybody has questions or they want to know more about just imaging service in general, I'll be here for a little bit getting my stuff together. We have a booth in the main gallery there. I think we're 102. We're basically the opposite end of the area there. But yeah, thanks for coming.